Hi, welcome back after what I hope was for you a wonderful Christmas break. A couple of things that I want to get taken care of before we start this chapter on circular motion, and that's the whole conversation about chapter 5. I was looking yesterday at PowerSchool and realized that that page that had the test on it was not published. I know some of you came in and grabbed the test while you were here, but some of you didn't have access to that, and so this has just turned into a nightmare. Even those of you that had access to it, I did not give you timely feedback on the homework because it just all happened way too fast. And so I'm really uncomfortable with how all of this played out. What I'm going to do with chapter 5 is I'm going to just call it all completion grades. You turned it in, you get a completion grade for it because you shouldn't be punished for the fact that I tried to hurry that way too much. And I apologize for that. Guys, I got to tell you that trying to do this remotely and trying to figure out all of this and the time frame for all of it and how fast I can get back to you, it's all a new ball game for me. And so I'm asking for your tolerance with that. And give me some feedback. How do you feel about me making those completion grades? If you didn't do the Chapter 5 test, I still want you to do it. I will make that page available to you. So just get it in before the end of the semester so that you can get the completion grade for that. All right, let me know what you think about that. If you have any problems with it, talk to me about it. Now let's get back into this chapter, and we're doing circular motion at a constant speed. That's the title of the chapter. And what we're going to be doing at the first part of the chapter is talking about actually speed and velocity kind of concepts, where it's distance and it's time, it's speed, it's velocity, it's acceleration. All of the kinematic things that we talked about in chapter 3, we're not going to talk about again, but we're going to put it in a circular environment. So there's going to be some changes, and certainly the terminology and the symbols for it are going to be different. There is posted on PowerSchool on the first page a Quizlet that you will have access to that can help you manage these symbols and terms. Absolutely essential that you're able to work through those, because once I start using these terms over and over and over again, if you're not familiar with what they mean or what symbol or what units go with them, you are going to struggle. So we're going to make, as the chapter goes on, we're going to make a chart with this. Try to keep up as you go with what the terms mean, what the symbols are, and what the units for those would be as well. So we're going to jump right into how we describe places or positions on a circle. Angular positions. First of all, we're going to talk about coordinates. Linear motion requires coordinates that are x and y. Super straightforward, just x and y, and I think I want to turn that into purple. So give me a second. I don't think that is purple. If it is, it doesn't look purple to me. Oh, it was purple, but I didn't like it. All right, so we're going to make it a little bit brighter here. Linear motion requires x and y coordinates, so that it goes from this position on xy to this position on xy. Just pretty straightforward. Circular motion requires coordinates along the arc length of a circle. That is called the arc length coordinate. And if you look at the circle on the bottom, what I'm talking about is, let's say that I start here, I travel from here, and I go to this position. My arc length coordinate then is going to be the coordinate along the arc length of the circle. This would be my arc length coordinate. The symbol for arc length coordinate is given, let me find where I am here, sorry. Symbol for it is given as S, and it's a lowercase s. I wanted to make sure I wasn't needing to say anything more about it. Lowercase s. Okay, again, two things that are brand new. Instead of calling it distance d like we would in kinematics, now we're calling the distance around the circle that you travel s, and it's called the arc length coordinate. Same idea as d in kinematics, but now because we're doing it in a different environment, we have to give it a different name. All right, now little letter a under that, this is a vector only in the sense that it's going to be negative for clockwise and positive for counterclockwise. That should seem familiar to you. Do you remember where we've seen negative as clockwise and positive as counterclockwise before? Think for about it a minute. It was in torque. It's the same protocol that we used for torque. Same as torque. All right, now, S, arc length. If it's a length, it's actually going to be measured in meters or feet or kilometers. The unit for arc length is going to be a unit for length. A different way that we can look at how much we've traveled around a circle is to look at the central angle that we've swept. How much of the angle of the circle have we gone through? The angle from the x-axis, I don't love this definition, to the arc, and by the way, the arc is actually, that angle is actually called theta, so that's my symbol right here, is going to be theta, is called the angular position coordinate. Angular position coordinate. And they can measure the same things, They can measure the same things, they're just going to measure it in two different ways. So if this is my center of my circle, then that doesn't really look quite centered, but we're going to pretend that it is. Then my arc length here is S, but my angular position is theta, and it's actually my central angle in the circle. So if I have another circle here, and my arc length is from here to here, because it doesn't have to be right on the x and the y axis. And I'm going to say that my center of my circle is right there. This is S, and this is theta. Measures the same thing. It's the same journey that I've made. It's just looking at it in two different ways. One looks at the angle that I've covered. The other looks at the distance that I've covered. Again, let me review. This is going to be my arc length coordinate measured in meters, kilometers, blah, 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 blah. This is my angular position coordinate, and it's going to be measured in, what do you think? Units to describe my angular position. Any guesses what the units could be? Units that you've used before. The most obvious one is going to be degrees. And I do this every time. I always forget to turn that off. First one is going to be degrees. And ask yourself, how many degrees are there in a circle? Hopefully you said 360 degrees in one circle. Another one is revolutions. And a revolution is just all the way around once. So how many revolutions are there in one time around the circle? Well, there's one in one circle. I'm going to put a little dot there so that it looks like a circle. And letter C, and I've got stars by this or asterisks by this because it is the most important for what we do. Radians. And if you've taken trig, then you are accustomed to radians. If you've done anything with a unit circle, you are accustomed to radians. And of course, I'm always talking about the fact that you've got to make sure that your calculators are in degrees and not radians whenever you're dealing with sine, cosine, and tangent for us. But you realize that that's two ways of looking at a circle, in degrees and in radians. For radians, there are 2 pi radians in one circle. This is the one that is most useful for us. It's going to be our go-to. Unless you're told to use a different measurement, you're going to want to use radians because almost everything requires radians. All right, the angle theta in units of radians is equal to, this is how you actually find it, S over R, where S is, you already know the arc length. That was from what we just did. How much of the circle have you traveled? All over the r is, like it is with any circle, the radius. This formula is theta is equal to s over r. This formula is kind of a big deal. It's the linchpin to everything that we do in this chapter. So I can find my angle in radians if I just divide or find the ratio between the arc length and the radius. Well, let's do an example of this. If my radius is equal to 10 meters and my arc length, S, is equal to 20 meters, then if theta is equal to S over R, what I really have then is that theta is equal to S, which is 20, all over R, which is 10, and this is meters, and this is meters. So theta is equal to 2. Now, if I have meters here on the top and meters here on the bottom, they just cancel out. It's a ratio. So this is very key. Radians is unitless. And I'm going to ask you to highlight that in your notes. It's really important. Radians are unitless. It's the only way that things work out the way they're supposed to. Anytime you have a ratio of the same measurements, meters over meters, newtons over newtons, anytime you have a ratio, then that ratio is going to end up being unitless if it's the same unit to start with. So that's my definition of radians. Theta is equal to S over R. Little letter B. For a complete circle, I want you to be able to show me how it is possible, and you can use your geometry for this, that theta is equal to 2 pi radians. Pause for a minute and play with it, dealing with the circumference formula. Okay? Hopefully you're back. Hopefully you're able to find that out. If I know that the circumference of a circle all the way around a circle, why is this not writing? All the way around the circle is 2 pi. That's just the formula for it. 2 pi r. If that's the case, that's going to be one way around the circle. It's all the way around. All the way around the circle is 2 pi r, circumference of a circle. So let's work through then. If the whole circle, we said that a whole circle is 2 pi, up here, the whole circle is 2 pi, then let's see how we got that. Theta is equal to S over R. All the way around the circle is my S, so I've gone all the way around the circle, so I've gone 2 pi r, my circumference, all over my radius. Look what happens to my radius. It cancels out. So all the way around, is equal to the circumference, which is equal to 2 pi r, which is equal to S in this case, because we said we were going all the way around the circle. So this is where the 2 pi actually comes from for theta for a whole circle is 2 pi radians. These relationships are important. Make sure you know them all. So it's 360 degrees is equal to 1 revolution, I'll do them in the order that you have them, is equal to 2 pi radians. All right, let's try the next section now where we're actually going to make some of these conversions, which, by the way, that's where you can write that. I apologize for that. So let me write that again. 360 degrees is equal to 1 revolution is equal to 2 pi radians. So let's do a conversion. 50 degrees is how many radians? And you can go ahead and use your dimensional analysis. So I'm going to have 50 degrees here. And 360 degrees is the same as 2 pi radians, and I don't want you to leave it in pi. When you plug it into your calculator, this is really, really important. This is not like in math. In math, you leave it in pi, and I understand that, and that's great. But physics is wanting to deal not with relationships, but actual numbers, so that you can hand it to an engineer. An engineer can hand it to an architect and say, it is this length, or it is this angle. And so actual numbers become important. So put in, click your pi button on your calculator when you're doing these, and you're going to find that it is 0.87 radians. That's your answer. And you're also going to be dealing with speeds of revolution per, actually these we call velocities, revolutions per second, and I want to convert that to revolutions per minute. So my revolutions doesn't change, so it's actually 14 revolutions in 1 second, and I want to know how many revolutions is it going to be in the 14. I don't want to change, but the seconds I do, and it's 60 seconds in 1 minute. Revolution just stays because RPM and R revolution, same thing. Do the math on that, and you end up with 840 RPM. Now I want to show you what you're going to do. Let's say that I had, I'll make one up here. And I don't have a calculator handy, so I'm just going to set this one up for you. And actually I do have a calculator here. I'm going to go ahead and do this for you because you'll have a homework assignment like this, and I want to make sure that you're understanding it. So let's say instead, you can write this on the back of one of your papers or just write it down on the side or somewhere. Let's say that instead what I have is, now let's make it 6 radians per minute is equal to how many RPMs? So I'm going to set the whole thing up, and I'm going to do all of my conversions at once. So and you can decide which one you want to tackle first, but if I have 6 radians, and I'm going to make this per second, so that you're having to convert 2 things. In 1 second, I'm going to attack my radians first, and I know that 2 pi radians is 1 revolution, so that's going to get rid of my radians here and here, and I'm going to be left with revolutions on the top, and I know that 60 seconds is 1 minute. Seconds and seconds. So you're going to take one piece of that and deal with it first. I first dealt with converting my angle into the proper terms from radians to revolutions, and then I converted my time into proper terms from seconds to minutes. Multiplying it across, and it's 6 times 60 divided by 2 pi. Give me a second. So it's 360 divided by, parentheses, 2 times pi, close parentheses, is equal to, and I got 57.3. And that's, yeah, that makes sense. So it ends up being 57.3 RPM. All right, keep that one in mind. You'll have one like this. Now I want to actually use the theta is equal to S over R problem, and that is 6.2. I'm going to simplify it a little bit. It seems kind of wordy, so I'm just going to break it down a little bit for you. What is the distance between two cities? They're both on the equator. Between 2 cities, one at longitude 48 and the other at 73 degrees, if the radius of the Earth is 6.38 times 10 to the 3rd kilometers. That I don't even think was written in the examples, so you'll need to have that. Because radius is part of the equation. So what they're saying is if you take a cross-section of the Earth, and this is the equator then, you're cutting the Earth in half, and this is the equator, and one of them is at 48 degrees longitude because the longitudes are going to run like this. So one of them is at 48 degrees longitude and the other one is at 73 degrees longitude, and I'm just making up where they would be. So let's say 48 degrees and 73 degrees. So I need to know, well, if I look at this, I actually know then my angle. I know theta. Theta is equal to 73 minus 48, or it's equal to 25 degrees. That sounds really awesome, and it feels like, well, that's super easy. Then I just plug it into my equation, but you can't. You can't plug it into the equation directly because in order to use theta is equal to S over R, theta must be in radians. It must be in radians. Please circle that, highlight that, make a big deal about that. Anytime you use this equation, you have to have it in radians because the definition of radians is S over R. Arc length over radius. Have to have it in radians in order to use that equation. It's the definition. So I've got my 25 degrees, but I need to put that into radians, so I'm going to do my conversion. 25 degrees on the top, and I know that 360 degrees is 2 pi radians. I do the math on that, and I find that I have 0.436 radians. Okay, so I know that theta is equal to 0.436 radians. And I know that R is equal to, it's in the problem here, 6.38 times 10 to the third kilometers. And I am looking for the distance between those two cities. So if I go back to my picture here, if my 2 points are here, I'm looking for this. If I know theta and I'm looking for this, I'm looking for my arc length. I'm looking for S. I know my radius, I'm looking for S. I know theta. That sounds like, and my theta is in now radians. It sounds like a perfect application of theta is equal to S over R, or 0.436 radians, which is unitless, is equal to S all over 6.38 times 10 to the third kilometers. Now, if my radius is in kilometers and this is unitless, then by design, this is going to be the same unit as my radius. So it's actually okay to leave it in kilometers. I don't have to convert it. If you decided to convert it to meters, it would just be times 10 to the 6th, but you don't need to worry about that because the units are exactly the same top and bottom. And when you do the math for that, you end up getting 2.78 times 10 to the third kilometers. 2.78 times 10 to the third kilometers. All right, now your homework tonight is going to be using this equation and just doing some basic conversions among the units for circular motion. Your homework is going to be 1 through 5 and 7 through 9. Okay, let me know if you have any problems with any of this. Again, if you're concerned about how I'm handling Chapter 5, you're more than happy to give me, or you're more than welcome to give me feedback. I'm more than happy to receive feedback on that because I certainly want to be fair with you folks.